Hello everybody, how y'all doing? We are gonna be doing lecture 2 for post midterm 2 material, and we only have, I believe, 4 more lectures, and that should wrap up all the material, all the lectures for COC 2. So congratulations for almost finishing. So we're doing now double integrals over general regions, and what that basically means is, if you remember from last lecture, the integrals we've been taking, our double integrals we've been taking, is if we have a plane like this and I gave you a section that was, let's say, something like this, right? And I told you, take this section, cut it into like 2 across or like 3 across this way, 3 by 3 or something, and then use like the midpoint rule and then estimate, right? And this is a square, right? But what if now the area I'm looking for is not a perfect square, but it's something like, so it goes straight and then it goes like that. And now the area I'm looking for is this. Okay? And so how do you calculate this? Well, this side is a straight line, this side is a straight line. However, this side is a function that's like, let's say rule x, this line is a function, right? And so that is what double integrals over a general region is that now we're not taking the integral from 0 to -4, we're taking the integral from 0 to root x, right? Or this is x, so it would be root y, I think. Okay, and so that's the whole idea. Now, how do you implement them? Pretty easy. I wouldn't say they're that complicated. So here, let's see. So this function, what it's saying is that take the integral from 0 to 1 of x. So let's draw it. All right. And so actually, I'm going to move these 2 lines. And so let's say this is my y, and this is my x. And so saying my x from 0 to 1. All right. My x is from 0 to 1. Now my y, it's saying from 0 to some function. So it's going to go from 0 to some function. I can assume the function looks like this. I know this is a root x, right? But just because, to be honest, I'm not sure what x to the power 3 even looks like. So that doesn't matter though. I'm just trying to visualize here. So I can make it look something like this. Like it doesn't matter, right? So let's assume this is my x3, okay? And now when I'm evaluating this, what I'll do is integrate. So I'm integrating y in terms of y. And so what I'll get is the integral from 0 to 1 of y squared over 2. And then the bound from 0 to x cubed. And I still have my dx. Right? Now you substitute this in. You'll get the integral from 1 to 0 of x to the power of 3 squared 2 dx. Right? And if I simplify this from 1 to 0, I'll get x6 over 2 dx, and then you can integrate this and plug in your bounds. And what we did here is we took the area under the curve. So right now this, we're looking at a plane, but we're looking from above. And now instead of us taking a square, the volume under the plane of a square, we're taking the volume under the plane of this shape. So we're taking this area now. But don't forget, this is a volume, so it's double integrals. Right, like this is not a general function like this, and I'm telling you find this, and this is in terms of x. Right? Usually when we're doing this, so if I have this, and I tell you find me the area under the curve, what I'll tell you is integrate my root x, right? But right now we're not doing this. What we're doing is, this is 3-dimensional. So this is actually the bound, not what you're integrating of. What you're integrating of is the plane function. So this y represents the plane function, and our bounds represent the area we're integrating of. And so our area just happens to look like this. Okay, so this is this part of the integration. Okay, and so, but what if the integral isn't set up? If we had a description of the region, how would we set up the integral? We'll go over that. Here says type 1, type 2. The only difference is that our type 1, so you see here, we're taking it from 0 to this line, right? And so this is how we set up our integral. Okay, now what if, I'm going to get rid of this so it doesn't confuse you guys. Okay, you need it, you can take a picture of it. I know it's annotated, so you don't even need to. This is 1. This is x. Okay. Put this so you guys know. All right. So now, so I'm taking this from 0 to x3, right? And I'm taking x from 0 to 1. So the strips I'm taking right now are vertical, right? You see, the change in my x never changes, or my bound in x never changes just from 0 to 1. But my bounds in y, as I am moving in the x, my height changes, because this is obviously my x cubed, right? So if I plug in the x here, it will give me the height of my y. Okay, that's why it's a function. Now, what if I want to switch them? And if you remember, Fubini's theorem said, so I'm taking this all the way to x to the power 3. Now, if you remember, Fubini said you could switch them. So what if I want to switch these? So I have the function y, but I want it in dx dy instead of dy dx. And so how can I switch the integral bounds? What I'll be doing is I'm solving right now from y, so from x 0 to 1. But if I wanted to flip it so that I'm taking the integrals like this, if I get rid of these, if I want to flip it, and if I want to take the integral like this instead, right? So I'm not doing a vertical anymore. I'm doing it horizontal now. Right? And so now if I wanna actually do this, so you see here I will have from, so this goes all the way up to 1. That hasn't changed. Okay? So see, now what I'm taking my bound is, I'm not taking the bound from 0 anymore. As this moves up, my x value changes, the bottom bound of my x value changes. And so let's say I tell you, well, I want my bound from y0 to now y1. Let's say I switched like this. And I say, well, give me the bound here. And so what I could do is I'll be like, okay, so my y is on the outside, so the integral on the outside, I'm taking it from 0 to 1. But the integral on the inside now, I am taking it x3, right? So x3 to 1. But the problem is, so you see I'm taking it from the line to my 1. But the problem here is that this is my dx. So this is x equals x3. Doesn't make sense. You want an x in terms of y. So what we'll do is we'll take this and we'll turn it in terms of y. Because remember, this x is y equals, right? So we're going to take our y equal x cubed, and we're going to turn it in terms of x instead. And so now x equals the square root of 3 y, right? And so now this bound will change to my root y3. I hope this clarifies things. And so that is our bounds of type 1 and type 2. So you see my type 1, I'm taking it vertically. Right? These are the strips I'm making. And type 2, I'm taking it horizontally. All right? And so pretty straightforward, nothing too spicy here. And it doesn't have to be one function. So you see here we're dealing with one function at the top. It could be 2 functions. There could be another function here, like an x squared from to the x, assuming we're not taking it like my y. So you see here, the bottom and the top are both functions. So this is just working with weird regions that are not just squares, or not just like you know. So you see, this is only, I only have one side that is weird, but sometimes you have both sides that are weird. Okay? And so if D is neither type 1 or type 2, you can break D into regions of D1 and D2, etc. Alright? I still haven't seen her give you an example like this. Maybe it will come on the midterm, but do keep in mind that if you can't integrate horizontally and vertically like this, if there was some weird situation, which I haven't seen any so far, but you could technically break them into 2 separate ones and then add them together. All right. And so remember to choose to treat something as type 1 or type 2 so that things are as easy as possible. You don't want to split a region up into several pieces if you don't have to, as that means doing several integrals. And that's basically saying, like, you see this triangle, I'll go like, you could go horizontally like this and split up the pieces, right? And the same thing here, you could go horizontally instead. But you see the problem here, can you guys notice? I'm taking my bound from a slanted angle to a slanted angle. So this, my integral, will be some function over some function. But this angle, this is a straight up line. So this is a constant number. So this is going to be number to a function. You see the difference? And so sometimes you could make it easier for yourself. Instead of making it like type 2, you can make it type 1. But if the triangle was like, you know, like this, then you see for here, you'd want to do a vertical, because this line is a constant. Right? So this would be number to function. Okay? Now, second thing to point out for this specific example as well is this triangle. So let me erase everything. So that's your first. So the first advice is that take it from the constant line, so it's easier. The second advice is that, so you see here, when we're doing this vertically, right? Type 1 is vertical, if I'm right. Yep. And type 2 is horizontal. Okay, so after I draw this, okay, so as you can see now, if I'm doing this vertical, the integral is going to be some function to some function. All right, let's change the functions. It's going to be g of x. Now, why is these two different functions? It's because this one is a line increasing, while this one is a line decreasing. So these are two separate functions. So I can integrate from the bottom function to the top function. But if I do it here, what I'm doing is constant to function. So I'm doing constant. I'm doing number, right? Number to this g of x. And I'll also have to split it in half. And I'll also have to do from constant to the second function, right? And I'll have to add them together. And so you see, this will get the same answer, except this one is a lot faster, because we are obviously going from two functions, one to the other, instead of number to function plus number to function, right? And so these are two advice. If you see a flat side, that's easy. That's usually the side you'd want to take. And the second thing is, it's better if you have, so if this was like, you know, something like this, right, where it's two right sides, then taking it like this or taking it like this is basically the same thing. Okay, but because this one going up, one going down, they're two different functions, two different functions that represent these two different lines. One is increasing, one is decreasing. And so, considering the region shown below, if we're finding the volume of a function f of x above this region, fill in the bounds. Okay, so as type 1. So type 1, we said vertical, right? This is what we're taking. And so we have dy, dx, and so dy comes first. What's my dy? My y goes from, so if I'm going y, I'm going from bottom to top, right? So I'm going from bottom function to top function. Bottom function to top function. All right, that's really how it is. And then my x goes from 0 to 2. Right? Your outside bound is always in numbers. Keep that in mind. Your outside bound is always in numbers. Okay? Because you want, obviously, a value. If this was another function, then you would not get values, and that should throw you off. Okay, and so second bound, now doing dx in terms of dy, we're going from left to right. So my left, so you read it from left to right. What's my first function on the left? This one, but obviously we have to put it in terms of x. Okay. And my second function is y equals x over 2. Okay, so now I'm reading it from left to right. Left to right. So my dx, which is this one, I'm reading it from left, which is right, to right, which is, and my y bounds have to be constant, so from 0 to 1. That's about it. As the integration is something we already know how to do, let's spend the rest of, setting up. Okay, so now we're evaluating this, where D is the region bounded by the parabolas. So I have this parabola and this parabola set up only. Now, how do we set this up? So we know D is some region on X and Y. Right? So the first thing is like, this is on X and Y, draw your X's and Y axes. Nice. So this is my X, and that's my Y. Okay? So it's saying, D is a region bounded by the parabolas. Y, so we have, it's saying it's parabolas, and we obviously have 2x squared, and we have 1 plus x squared. And so because of this one, I know one parabola starts higher than the other. And so I know one parabola, so if I make this more realistic looking, actually I don't need the bottom one, I just need that one. Okay, and so I know one starts at 1. Okay, so one parabola looks something like this. And my second parabola just is a little bit skinnier. Now, you're probably going to wonder, oh my god, what if I don't know? So this is 2x squared and 1 plus x squared. And you're probably going to think, oh, what if I don't know, like, how to graph these? What if I see a function and like, what? I don't know, like, what I'm looking at. And so what you can do is you can always just set, what do you call it? You can always just set the function like x to 0. So you can make this 0. That gives you this as 0. That's my first interception, right? As 0. And so I could set this to 0 and my y is at 1. And I know that's my second interception. Now you can put your y at 0 and you'll find your x-intercept. You can, but I don't find that as helpful here because it's parabola. So you should know this opens up. Okay. And so that's how you could find out like where they start. Now, if you recall, we did say that the outside bound has to be a numeric answer. And so first, let's set the inside bound, then we'll set the outside bound. So my inside bound, right? So let's say we have my x plus 2y. And let's say I have dy over dx. Or you can do dx over dy, up to you. We're going to do dy over dx. And so my bound for the y, I am reading it from bottom up. So you see, even when we're here from bottom up. So from bottom up, we know 2x squared comes first. And then going up, it's 1 plus x squared. All right. Now, my second integral, what is the bounds? Now, if you remember, we are looking for the area under the curve, right? Or area under the plane. And so the area I'm looking for, so if this was the actual area, so right now I just drew it, I'm going to erase this, and I'm going to show you how this would actually look like when I'm looking for the area under the plane. What they're actually saying is I have some parabola that looks like this, and I have a second parabola that looks like this. And it's telling me, find the area. This is the area I'm looking for. Right? Because they're not going to have your area as open-ended like this. Right? Because, like, what is this? Okay? And so I hope that makes sense. So what they're actually doing is they're saying one parabola goes like this, and we have a second parabola that goes like this, and then this one is my 2x squared, and this is my 1 plus my x squared. All right? And now what we want to find is, as you can see here, where they meet is the points we took from 0 to 2, or from 0 to 1. You see my bound was 0 to 2 or 0 to 1. Now it's the same thing here, where they meet. Right? Now if you have two functions, how do you find where they meet? You just set them equal to each other. Alright? And I can solve my x so I can find out where they meet. Okay? So if I solve for my x here, what can I do? So whoops. I had an error come up on the computer for some reason. But okay, so we're going to take 1x to the other side. So we have 2x squared minus x squared equals 1. Right? Minus. So this will become x squared equals 1. And now if I square root, I will get a plus 1 minus 1. And you see now these meet at -1 and 1. So these are my bounds. -1. So obviously we read from left to right. -1 to 1. And that's really how you do it. Now you could do it like we were saying earlier, where you could flip it. And so you see right now we're taking horizontal. Now you could flip it and you could start taking vertical. Oh, sorry, horizontal. We were taking vertical. Let's say we start taking vertical like this. But as you can see, if we did it like this, we would have to split our bounds, because you see here we're taking it from this edge to this edge, which is the same function, but on here we're taking it from two different functions, which is now we're taking the bounds from this is now two integrals. And so obviously use common sense and see which one just makes more sense and which one is easier to integrate. And so I was like, as soon as I did this, it just looks wrong, like it doesn't make sense. I'm taking the bound from an integral to an integral. So I hope that clarifies things. Find the volume of the solid that lies under the parabolic, whatever this is, and above the region D in the xy plane, bounded by the line this and the parabola this. Setup only. Nice. So like we said, if you're looking volume under, you always want to just look at it from above. So the z actually doesn't matter, because right here we're looking at z0, right? And so at z0, so it says find the volume under this. So we know we have, this is the plane. This function is your plane. This function is your f, x, y. All right? And so this function equals your x squared plus y squared. Okay? And so now what they're saying is we have a line to x and the parabola y equals x. So if we set this to 0, we set to 0, we know they meet at 0. We put both x and y at 0, we know they will meet at 0, right? And then it does say 1 is a line. That is a line. By a line. And the parabola, this. So this one. Obviously, we know a parabola that starts like this, and it will go up, and they will meet somewhere. Okay? And now, if we want to know where this somewhere they meet at is, 2x equals x squared. Right? And so now you just isolate. So divide by 2. Divide by x. You'll get 2 equals x, and that's your second one. Right? And so now that we found out two bounds, we can set it up. So we have the integral. The first integral, we're going to do x, which is from 0. So here, you can either do vertical or you could do horizontal. Okay? It really does not matter. If you want to find your y bound, what you'll do is you'll take 2, so 2 up here, and you'll sub it into the equation, in either one of the equations. So I could sub it here. You see, if I sub 2 here, I'll get a 4. And if I sub 2 here, I'll get a 4. And so when you sub it, you'll get 4. And so if I'm doing dy first, so let's say I'm doing dy first, dy will go from 0 to 4. My integral for the dx, so this will be x squared plus y squared, we said dx, dy, right? Dy for this part. Okay, now my x, I am going from the line, right? You read it from left to right. I'm going from the line, which is 2x, to the parabola, which is x squared. And that's your setup. Okay, And now rewrite the integral with the order of integration changed. So now when you see this, it's like, well, now what we're trying to do, we're trying to change the order. How can we change the order? You can just visualize it. So like I said, you always want to just draw this. This helps you like make things so much easier. And so I have my y, and I have my x. Now my first integral on the x goes from some function. So I don't know what this function looks like. I'm gonna just boom. I have no clue if it looks like this. This is just a guess. All right. The whole point of this is to visualize. So I know I'm going from this function to my 1. Right? Because dx comes first, this is the amount for dx. And I know my dy goes from 0 to somewhere along 2. Now I want to flip these the way I want it. So right now I'm doing horizontal. Dx comes first. So I'm doing horizontal. This is how I'm taking it. Now what I want to do, I want to take it like this. Okay? And so if I want to take it like this, what I'll say is the integral. Right? I'm just going to write empty integrals. 3, and then I have dy dx. Now I do know the outside bound, the dx has to be a numerical. And I know my x bounds from 0 to 1. Right? Now, how do I know it's 0 to 1? I actually don't know. So let's check. If I take, so if I have, this is my x, and it goes from 0. Oh, sorry. It goes from this function to 1. But we don't know where the function starts. So how do we find it? What we can do is sub in. So I know my y starts at 0. So if I sub in 0 for this, because this is x equals y over 2. If I sub in 0 at y0, I will get x0. So now I know actually they do both start at 0. That's how you can confirm. And so I know now the bound of my x is from 0. And I know it's 1 because up here it says, x goes all the way to 1. So that's how you know. Now for my y, which is these bounds, my y, instead of before, because I was taking it horizontal, I'm going from 0 to 2. Now I'm taking it vertically, so I am going from 0 to the function. Right? So I'm going from 0 to the function. But the function is x equals y over 2. I want it y equals something. So I'll just take to the other side. Right? And so this becomes 2x. And that's really how you could visualize it. That's really how you can do it. It's not too hard if you just practice a little bit. And now it says find the volume of the solid bounded by planes this. X equals 0, y equals 0, and z equals 0. Like I said, always, if we're looking for solid volume, draw your x's and y's. Oh, look how straight that is. Oh my god, so hot. Okay, so if I said for z, because obviously we want our z equals something, because that's your f of x. So you gotta isolate for z. So our z equals 1 minus x minus y. Now this equals my f at xy. Okay, and so now we're just gonna set this as my y, set this as my x. And what do they want? They're saying my y equals 0. And they're saying my z equals 0 and my x equals 0. And you give us some function. It says find the volume of the solid bounded by the planes. So it's bounded by this. And I have x is 0, I have y is 0. And now I gotta obviously find my other bounds. And so how can I do that? Now, as you notice, they do give us a visualization. So even if you don't have this visualization, you could still do it. I'm gonna use it to explain it, help you understand it better. Okay. So what they're saying is this is bounded by x at 0, y at 0, and z at 0. And this part is very important. Why? Because this plane, if I was looking at z equal -1, you see my volume is completely different. Because now I'm taking the volume under the plane, which is this whole plane. You notice that? But I'm not doing that. I'm doing z at 0. So if you look at it, the plane I'm only taking under the curve is this part. Right? That is the only part I'm taking. And that looks like a right-hand triangle. I believe this is a right-hand triangle. I'm not even sure. right angle triangle. I don't know, I said right hand. Right angle triangle, right? And so that's one way to do it. The mathematical way, if you didn't have a picture, is since you know that you want it at 0, you'll set your z at 0 and you find your function. So z equals 1 minus x minus y. Right? Now I can take x to the other side and get my function in terms of y, or I can take my y to the other side and get my function in terms of x. I'm going to do the y one. Right? Now, if I want to set up my integral, I'll have a double integral. Right? And then I have 1 minus x minus y. And then I'm going to do, let's see, since I already have this, I'm going to do dy first. Because I know my first integral can handle a function. My second integral have to handle numeric values. Right? And so I'm going to do dy first and dx. Now, where am I going? I'm going from where to this line? Okay, so I'm going to try to do this mathematically first. So we know we're going from y0 to y1 minus x. So if this looked like 1 minus x, and I know this is a down line because if you just have x, that's not squared or cubed or square rooted, it's a line. And because 1 minus, that means it's a degrading, like it's going downwards. That's how I know this, okay? So this is my 1 minus x. Now, if I was taking it, so you see, if I was taking it type 1, I would go from vertically, right? Type 1 is vertically. And so I know it does tell me y equals 0. So I'm going from y0 to y1 minus x. And so I'm going from y0 to 1 minus x. Now, what is my values for x? And so I do know that when well, obviously I do know my x starts from 0, but where does it go to? I know because it's going downwards, it's going to go to y equals 0. When I set this to 0, then my x equals 1. Right? And so that is my top bound. Okay. Now the question is, well, how do you know if you didn't have the visual image? Well, you will have this function. You'll have to isolate for z anyway. And now if they give you a z, then you know, obviously you have to sub this in. This is just something that you'll always do. If they give you a z value, because obviously depending where the z value we're taking, I'm taking the z value up here, obviously, I'm taking the z value up here, obviously the area under the plane is only this section, because everything else is under that z value. And so that's why you'll always plug in, because and in certain planes, it depends heavily on where your x is, where your z is. So you see, like, if you put your z at -1, or if you put your z at -2, that would give you the same value. But that's not always the case, and that's why you always plug in your z. Okay, then you'll get some function. Now this sum function, you can either put it in terms of y, or you can put it in terms of x. Either way, whatever you put it in, you'll sub in your other numbers. So since this is given, if it's in terms of y, you know you start at 0 and you go somewhere. And if you got this equation, you'll know you start at 0 and you'll go to this equation. Okay? And for your x, you just sub in, you know you're going at x0. You just want to find out your y. And so since you already have a y0, plug it in and you'll find your number. Okay? So that's if you don't have a visualization. All right, so now trying to solve for this, what you do, first things first, same thing. I'm gonna try to fly through this. Oh, what happened? So much so for flying through it. Okay, z. I set for z, so I'll get 2 minus x minus 2y. And using this graph, we're looking at it from the top. It looks something like this. Right? And so what we're gonna do, well, actually, let me have a better drawing. There you go. Okay. And so if we're looking at this, we do have our first function 2y, and that is so this is, because this is positive, it's a line going upwards. So that must be this line. Okay. So this is x equals 2y. All right. And then what's my second one? I'm going to set my z to 0. And solve for x. Okay. And so this is negative. That means my y is, so this. Right? Now I will start my integral. I'll have some integral. And then it's 2 minus x minus 2y. And then I have some d. 2d's. And now I want to find the integral of these two bounds. Now, which one goes where? What I want to do is I want to set my y first and my x later. Why? Because I already have one bound for x, which is my 0. Okay? The second thing why I want to do that is because if I take it horizontally, then I will be taking it from constant to function. Then after I reach halfway, I'll take it from constant to different function, and that's two different integrals. Or I can take it vertically, which is just from one function to the other, right? And so what I'm going to do is a type 1. And type 1, your dy comes first. And so what this will be is I'm going to change these two functions in terms of y. Right? Okay, so I took negative 2y to the other side became positive, took x to the other side, now it's 2 minus x, divided by 2, this is what you get. Now these are my bounds, but which one goes to where? We're going from bottom to top, so to top, so 1 minus x over 2. And that's your bound. Oh, we still got our x, forgot about that. So if you want to find out where they meet, you just make them equal to each other. We went through this last slide, right? And so now you gotta solve. So I'm gonna take this to the other side, equals right, and that's my top bound. And that's about that's the done. That's about it. Thank you guys for watching. Hope it helped.